Hi everyone, welcome to my channel. In the previous video we have discussed the fundamental building blocks of linear algebra, vectors, how we can represent vectors in some of the basic vector operations such as vector addition and vector scalar multiplication. We have not yet talked about dot product and cross product of vector. We will be discussing that topic later in the course before we have an idea about how linear transformation works in context of linear algebra. Now we are starting our discussion on matrices. In this tutorial we will talk about matrices and their basic operations, and in the next tutorial we will relate it to linear transformation, which is really an important concept in linear algebra. So stay tuned, keep watching. If you are already familiar with basic metric operation, you may skip this video. So let's talk about what is a matrix and how it is useful. So if you are not from math background, but if you have done some programming before, you might be having an idea that many times you need two-dimensional data structures to store your data. So in programming language, we say that to store two-dimensional data structure, we need to have rows and columns, right? And what earlier we have seen vector, it was one-dimensional data structure. So if you are from programming background, then you might be knowing that if you store a data in the form of a list or array or vector, something like this, so it is suppose 32 and 36 and 38 whatever, then this is just one dimensional data structure because you have information only in one dimension. This can be different variables. For example, you are saying that 32 is age, 10 is years of experience, and qualification is PhD, whatever. So you are storing information of different variables but in the form of one dimensional array or list, right? Then in linear algebra you can refer it to vectors, which we have discussed, and in vectors we have seen that you can have 2, 3 or more than that dimensions as well, right? And now if you want to store the information of different variables for different people, for example, if you have a data of 10 respondents, so for 10 samples you want to store their age, you want to store their years of experience, you want to store their qualifications and many other things like that, then you need to use a structure like this where you have first sample here, second sample here, third sample, up to 10 sample or whatever number of sample you have. This kind of data can be stored in a matrix. Now if you are from programming or if you use R and Python, you might be in a habit of using data frame also. In R it is inbuilt data structure, in Python you use pandas to have data frame data structure, right? So we are not talking about those data structure right here, but we are giving you what does matrix mean in mathematics or in linear algebra. What are the basic metric operations and how these are useful. You might have used matrix before without even knowing it in depth, like if you are doing image processing or image classification, there also you store the images in the form of a matrix where you have pixel intensities here as the entries of your matrix, right? So many times you work with matrix without even knowing that. If you are using linear logistic regression, something like that, so you have the predictors here, you have the outcome variable here in the last column, and you do some manipulation with the matrix. So behind the scene it works, and it is always good to have an understanding so that you can understand your algorithm better. Now let's talk about matrix in mathematics. So in mathematics, again, matrix is like this, where you have rows and where you have column. And suppose you have here m rows and n columns. In context of symbols, if I am writing, if you have m rows and n columns, so your rows will be starting from 1 up to m. So this is A21, A31 and up to AM1. These are the elements of your first column for all the rows. Similarly, in the second column, you can have elements A12, A22 up to AM2. And similarly, in the last column, you might have elements which can be denoted by A1n and up to AMN. So this is how mathematically you represent the matrix, and these are the elements in that particular row and particular column. So suffix aij, you can also write it like this, matrix of elements aij, and these I represent rows and j represent columns, and I is going from 1 to m, j is going from 1 to n. So these are just the mathematical way of writing it. If you are not comfortable with the notation, it's completely okay. You should have an understanding of what is a matrix and how it works. And usually we denote the matrix by some capital alphabet, A, B, C, M, T, whatever, right? So these are the matrices. Now let's talk about basic metric operation. So metric transpose means you just reverse the orientation. For example, if you have a matrix in which these are the elements 4, 5, 6, 7, 8, 9. So this matrix, if I ask you what is the dimension of this matrix, dimension means number of rows and number of columns. So it has 1, 2 and 3 rows and it has 1 and 2 column. So we can say this is a 3 by 2 matrix, right? This is how we represent 3 by 2 matrix. Now if we want to find out transpose of this matrix, suppose this matrix is matrix A. So A transpose would be just reversing the entries and changing the rows and columns. So it would be now having 2 rows and 3 columns. And how we will write the elements? This is like 4 and 7. It is now becoming a column. 5 and 8, it is now becoming another column, and 6 and now becoming another column. So this is the transpose of the matrix, and the dimension becomes 2 by 3. Right? So even if you are not comfortable with the notation, you can understand that you are just flipping the dimensions here. Or if you are comfortable with the dimensions, you can now see that the transpose of the matrix A, we denote it by the symbol A transpose or A prime. Also we can write A prime like this. This is nothing but the matrix of AJI. Right? And where we have changed the values of J and I, it is n cross m matrix, so it is reverse matrix. But don't worry about the symbol as of now. You can work around with any bigger matrix and you can see how the transpose works. Now let's talk about matrix addition. If you want to add two matrices, right, then how you can do that? For example, this is your matrix in which you have element 3, 2, 5, 7, 1, 9. And this is another matrix in which you have elements, for example, 2, 3, 1, 5, 6, 4, whatever. I am just writing any random numbers. To add these two matrices, you just need to do element wise sum, right? But to be able to do element wise sum, there is one condition which is to be met, that the dimensions of these matrices should be the same. So this matrix is 3 by 2 and this matrix is also 3 by 2. Then only you will be able to perform element wise addition, right? And the elements, if you add, it would be, let me change the color. So it would be first 3 and the corresponding element 2. So 3 plus 2 would be here, then 2 plus 3 would be here. And similarly, you will have 5 plus 1, which is 6, 7 plus 5, 12, 1 plus 6, 7, and 9 plus 4, 13. So this would be your resulting matrix. You can write 5 and 5 here, right? And the dimension again is same. So matrix addition works when you have matrix of same dimensions. And how it works is you add element wise. For example, the first matrix denote price of some product. Suppose this is matrix A and this is matrix B, and in matrix A you have price of some product, in matrix B you have packaging charges for some product. And if you want to see overall cost, so it would be matrix A plus B. Suppose you have additional shipping charges in another matrix C, so you can add plus C also. You can define another matrix and you can add C. But to be able to do that, you need to make sure that dimensions are same. If you want to see how it works mathematically, you can write this formula in terms of symbols. Suppose this is A11 up to A1n and this is AM1 up to AMN. And another matrix you can write in terms of B11 and B1n, BM1 and BMN. Then the sum of these two matrices would be, first element would be A11 plus B11, and similarly you have all these elements here, A1n plus B1n and so on, right? So there is no need to write every time in terms of notations, but you should have an idea how you will work given a problem of this kind of thing. Now matrix subtraction, it is again very simple, and you might have guessed, we just subtract the elements from the corresponding elements. So suppose this is my matrix 10, 8, 2, 0, and another matrix is 6, 4, 2, 3, or we can have negative elements also. So if you want to do this subtraction, you will subtract element wise. So this would be 10 minus 6, which is 4. Next element would be 8 minus 4, which is 4 again. Next element here would be 2 minus 2, which is 0. Next element here is 0 minus minus 3, which is plus 3. So this is how you will do matrix subtraction. Now matrix scalar multiplication. So scalar, you might be already knowing, it's just a number. So how you multiply a matrix with a scalar? So for example, this is your matrix and you want to multiply this matrix with some scalar. For example, you want to multiply it with 2, then you will just do element wise multiplication. Means if it is 2, you will double all the elements. So let's multiply 2 by 14. This is 28, this is 20, this is 4, 8, 10 and 4. This is how you will do matrix scalar multiplication. This number can be any real number. It can be a positive, negative number, integer, floating point number, whatever. So suppose it is 1 by 4 here and you have this matrix 20, 30, 60 and 100. Then again you can do, and it depends if you want the result in terms of fraction or if you want the result in terms of floating point number, you can accordingly write. So it would be 5, it would be 15 by 2, or you can say 7.5, it would be 15 and 25. So this is your resulting matrix. So it can be a factor also. And how we represent matrix is usually given by some capital alphabet, and scalar usually we represent by small alphabet. So this is suppose your A, this is capital A, something like that, right? And alpha, beta, gamma, these notations are also used sometimes for scalar. So these are very simple things, but we need to know these calculations before we move ahead to some important topics. Now let's talk about matrix vector multiplication. So now you know what is a vector, now you know what is a matrix, and you want to multiply these two things together. So how that works, I will show you first of all mathematically how it works, what is the formula or how you do the computation. But we will also discuss its geometrical interpretation. What does it actually mean when we are doing matrix and vector multiplication? So for example, I have a matrix A and this matrix is 2, 1, 0, 0, 1, 0. I have vector V, 10 and 20, right? And if you want to multiply A with V, so basically you want to see, excuse me for this line, somehow I can't erase this. So you want to see A multiplied by this vector B. How that work? So without writing the formula, let me show you the calculation first so that you find it comfortable. There are many who just get scared when we write in terms of notations or formula. So don't worry about that. You just need to know the pattern how you do the multiplication. And in the next tutorial, we will see that what actually it means, what is the interpretation and how we do these kind of things. So this is a matrix, this is a vector. How you do is you first start with first row of the matrix and you take the vector column. Obviously it is a vector, so it has just one column. And how we need to do is we need to multiply the corresponding elements and add them together. How it works, let's see. First of all, we will multiply 2 with 10. So first element we will multiply. Then we will multiply 0 with 20 and we will add these two together. So this is 0 multiplied by 20. This would be the first element of the resulting vector. Result would be a vector always. When we multiply a matrix with a vector, result would be a vector. So we can write it like this. A multiplied by V would be some another vector W. And we want to see what is the vector W, right? Now we will look at the second row of the matrix. Second row is 1, 1. Again we will multiply these elements with the corresponding elements of the vector and we will add them together. So it would be 1 multiplied by 10 plus again 1 multiplied by 20 because the next element is also 1. Then the last row is 0, 0. I should have taken different element. But anyways, I hope you are getting the idea how we are multiplying, how we are adding. So this pattern we need to follow, and this pattern would be applicable in matrix multiplication as well. So we will take row and we will multiply with the corresponding column. We will add the entries together. So the output would become, this is 20 plus 0. 20 would be the first element. Second element is 10 plus 20, which is 30. And the next element is 0 and 0. So this is 0. This is the resulting vector. So here we have done matrix vector multiplication in the form of numbers so that you can understand the pattern. Those who prefer understanding the formula first, let me write the formula also. So suppose you have a matrix which is like this. A11, A12, this is A21 and up to, let me write the general matrix A1, M1, This is A2 to AM2. We don't need to write all the elements. So this is A1N, A2N, AMN. So this is the matrix A, and suppose we are multiplying this matrix with a vector. So vector can be here, suppose I am taking the vector ux, uy, uz. These are the coordinates. Oops. Yeah, we need to make sure that the number of elements in the row of the matrix should match the number of elements in the vector, right? So if we have n elements in the rows of the matrix, dimension is m by n. So if this is n, or we can say how many columns are there, there are n columns. So there should be n elements here in the vector so that we can multiply the corresponding elements. So instead of writing ux, uy, uz, let me write it like this. u1, this is the coordinate with respect to the first axis, u2, and suppose we have n dimensions, so it is un. And we want to multiply these things. So my matrix is A, my vector is U. We can also write V, sorry for the inconsistent notation. And if we multiply, what happens is we need to multiply the elements of first row of matrix with the vector, and we need to add those. And how that work will? So look at the first row, multiply these with these elements and add them together. So this result would be just a vector. But in the vector, we would be having m rows, right? So first row would be A11, U1 plus A12, U2, and so on up to A1N, UN. And if you don't find these formulas very intuitive, you can just write the formula for a small matrix, for example, a 2 by 2 matrix and a vector of dimension 2, so that you will be able to relate to it. And similarly, you can write the formula for the next row. It would be A21, U1 plus A22, U2 plus, and so on, A2N, UN. And so on. Last row would be AM1, U1 up to AMN, UN, right? So this is a vector of dimension m. Otherwise, you can also write it like this. Suppose you have a matrix like this, x1, x2, x1, x2, y1, y2, and you have a vector, suppose A and B. So the sum would be, the vector matrix multiplication would be, you are just writing ax1 plus by1. This would be ax2 plus by2. These would be the elements of that vector. This is for a smaller matrix. Those who are finding this formula is difficult to read, they can just understand by looking at the formula on the right hand side. This is for a smaller matrix, and we can always generalize the idea for whatever dimension we have, right? But if you are comfortable and you can write this kind of a formula, you will also get an intuition about the dimension, that your matrix A was m by n matrix, your vector U was n dimensional vector, and your resultant vector was m dimensional vector. So those who are comfortable with notation of algebra, like we write in terms of function, you get an idea that for this particular operation, the input spaces of this dimension, because this is the size of your matrix and this is the size of your vector. And I hope you understand this notations if you are from mathematics, that this is the space of this dimension, space of real numbers is space of real numbers, and the output space is of dimension Rn. So it is always a good thing if you understand the dimensions of input space, output space. I hope those who are from mathematics can recall that how we define domain, codomain, and image of the function or transformation, because this is going to help you to understand in-depth concept about more properties of such operations. But if you are not from mathematics, don't worry about whatever I have written on this slide. You can just look at the previous slide where we have done this kind of a calculation. And this was again just the formula. And don't worry if you don't even want to do these kind of stuff, because there are tools, there are softwares which will do these tasks for you. You don't need to do these things manually, right? But what is important is you understand that first thing, dimension should match. If you are doing these operations in Python or R and you are getting some error, then you might need to make sure that you are doing the operation for the right dimension. Second thing, you should have an understanding of why we are studying matrix vector multiplication. Is it somehow useful? What is the geometrical interpretation of this aspect? So we are going to talk about the interpretation of this particular operation in the next tutorial. Stay tuned. Thank you for watching.